buenas tardes a todos. Bienvenidos a esta conferencia, que pertenece al quinto ciclo de conferencias en Astrofísica y Cosmología de la Fundación BBVA. Es para mí un honor hoy presentar al profesor Werner Hofmann del Instituto Planck de Física Nuclear de Heidelberg, que nos va a hablar del estado de un campo nuevo y vibrante, la astrofísica con rayos gamma de muy altas energías. En primer lugar, quería dar las gracias a la directora del ciclo, la profesora Ana Chúcarro, por su labor organizando estos ciclos de conferencias. Y también, de modo más amplio, quería agradecer a la Fundación BBVA, a través de su director, el profesor don Rafael Pardo, la tarea apoyando la ciencia y la física en particular. Creo que nuestra sociedad lo necesita y lo agradece. Y que está clara la asistencia a estas conferencias, que siempre están hasta arriba. En segundo lugar, quería presentar brevemente al conferenciante. Como pueden ver en el currículum que acompaña el programa de la serie de conferencias, el profesor Werner Hofmann nació en Baden-Baden, Alemania, estudió física en Karlsruhe, doctorándose en 1977. Obtuvo la habilitación en física en 1980 en la Universidad de Dortmund. Entre 1982 y 87, según mire uno, impartió clases como profesor en la Universidad de California en Berkeley, donde fue nombrado catedrático. Y desde 1988 es director de investigación en el Instituto Planck de Física Nuclear de Heidelberg. A lo largo de su carrera ha recibido numerosos premios, no los voy a decir todos, pero cito entre ellos el Premio Rossi de la Sociedad Americana de Astronomía o el Premio Descartes de la Comisión Europea. Y a estas cosas, a estos datos del currículum, quería añadir un par de apuntes propios, y es que conocí al profesor Hofmann a principios de los 90, cuando entré a trabajar en el experimento EGRA, que operaba un conjunto de detectores de rayos cósmicos y gamma en la isla de La Palma. Su trabajo en EGRA, introduciendo la observación estereoscópica, con varios telescopios a la vez, le dio el empujón definitivo a la técnica Cherenkov, de la que nos hablará hoy probablemente, al aumentar su sensibilidad de forma decisiva. Somos capaces de ver muchas más fuentes porque controlamos mucho mejor el ruido. Tras EGRA, el profesor Hofmann fundó la colaboración GES, que construyó un observatorio Cherenkov en Namibia y lo sigue operando hasta hoy. He de decir que, a pesar del desafío de construir un observatorio de alta tecnología en una zona muy alejada de la civilización, GES ha sido el observatorio de astrofísica de muy altas energías más exitoso del mundo. Ha cartografiado la galaxia en muy altas energías, ha descubierto emisión de numerosas galaxias activas y ha obtenido resultados importantes en física fundamental en temas como la búsqueda de materia oscura. Desde el año 2007, el profesor Hofmann es el portavoz del consorcio que construye la red de telescopios CTA, en la que trabajamos más de 1.200 investigadores, para construir la nueva generación de observatorios Cherenkov. A lo largo de estos años siempre me ha impresionado su profundo conocimiento tanto de la instrumentación como de la física y su capacidad de organización obvia y manejar estos consorcios. Además, doy fe de que es un excelente conferenciante, como tendremos la oportunidad de comprobar hoy. Por último, quería comentar la importancia que algo en apariencia tan exótico como la astrofísica con rayos gamma de muy altas energías tiene para España. Hace ya casi 30 años, a finales de los 80, cuando aún no se conocía ningún objeto que emitiera este tipo de radiación, ningún objeto cósmico, un grupo de centros alemanes y la Universidad Complutense decidieron aprovechar la infraestructura existente en la isla de La Palma, que se había levantado para dar soporte a los telescopios ópticos, e instalaron entonces en el Observatorio del Roque de los Muchachos los detectores del experimento EGRA que he nombrado. Desde entonces, el Roque ha sido siempre uno de los principales centros europeos de lo que llamamos física de astropartículas. Para mí es una muestra clara de que cuando se siembra en ciencia siempre se cosecha, aunque sea a veces de formas inesperadas. Esto se montó para los telescopios ópticos y hemos acabado haciendo física de rayos gamma también. Tras EGRA, en paralelo con el observatorio GES, el observatorio MAGIC lleva operando en La Palma más de 10 años y ha obtenido también resultados muy relevantes y complementarios a los suyos, ya que observa el cielo del hemisferio norte mientras que GES observa el del sur. MAGIC cuenta con una importante participación española. Estimo que la comunidad española que trabaja en MAGIC y CTA está formada por algo más de 100 personas, un número grande. Actualmente el consorcio CTA ha decidido construir en La Palma uno de sus 2 observatorios, el norte, y va a ser una de las infraestructuras científicas más importantes que se construyan en España. Las obras ya han comenzado, las podéis seguir a través de una página web, podéis ver cómo van progresando, el primer prototipo, y estoy seguro que en los próximos años oirán hablar mucho más sobre este tema. Es por ello que agradecemos especialmente otra vez la presencia del profesor Hofmann y su disponibilidad para dar una conferencia que es importante no solo para el conocimiento de la ciencia en general, sino también en este caso para su avance en España. Así que, sin querer robarle más tiempo, paso la palabra al profesor Hofmann y espero que disfrutéis de la belleza de la técnica experimental y de la física que nos ha permitido descubrir. Muchas gracias.
Well, thank you very much for the invitation to present our work here. Thank you very much for your interest. What you've just seen is one of the telescopes which we are operating in Namibia, and what I want to use this evening for is to tell you a little bit about the things we see in the sky with these telescopes, which give us new visions of our galaxy. So, of course, you all know these wonderful pictures which optical telescopes deliver of the sky. They're just great, but one should also be reminded that the optical light, which we see, the light which we see with our eyes, which ranges from the red light to the blue light. Red light has low energy per quantum, low frequency. Blue light has high energy, high frequency. That the range covered, the frequency or pitch range covered by the optical light, which we see with our eyes, is actually just, if I compare it to a musical analog, is just 1 octave on a piano. Now, from space, we receive electromagnetic radiation. Light is electromagnetic waves over a much larger frequency range. And in fact, if you stay with the analog of acoustics, what we see from space is radiation encompassing 70 octaves of the spectrum, meaning the universe out there is playing on a 15-meter-long piano. And much of modern astrophysics has been to expand the way we see the universe from the 1 octave of the visible light to as wide a range as possible. And it turns out that it's required to really understand what's going on out there. And let me illustrate this with a very simple example, again, taken from acoustics. What I want to do is I take a familiar piece of music and I cut out just 1 octave of the frequency range. So that's like the visible light which we see from the universe. So let me just place this. Let me see if it works. So this is music, 1 octave. It sounds horrible. You don't recognize what it is. Whereas if I now switch to the 10 octaves of normal music, which our eyes hear, you immediately recognize what's playing there. And so this is really, it's the same thing with modern astrophysics. You need to cover all this frequency range to really appreciate what's going on out there in the universe. So, of course, beyond this scale of electromagnetic waves, there are other messengers. There are gravitational waves, there's neutrino radiation, there's cosmic rays, which all cover similar frequency spectra. But at least so far, only light, electromagnetic radiation, provides images of the universe, which is why much of the effort concentrates on these electromagnetic waves. And what I'll be talking today about is sort of the rightmost 2 meters of this 15-meter-long piano, which is something which only in the last decade we've sort of understand to listen to. So that extends the sounds which we hear from the cosmos, so to say, to the very high-pitched sounds, to the very high-energy quanta. What makes this range particularly interesting is that normally the frequency or the color of radiation depends on the temperature of the emitting body. If you see red light, it comes from something which is around 800 degrees hot. If you see yellow light, it comes from something which is 1200 degrees hot. Now you can ask how hot has something to be which emits light or radiation, at this very rightmost end of the spectrum? And the answer is there's nothing hot enough in the universe to create such radiation. So it has to come from some other means, which is why we call this the non-thermal universe. It's the universe of radiation which is made by some other means than just hot stars. And one of the issues is, what is this universe? What are the particles in it? How is this radiation generated? And this is what I want to tell you about today. Now, of course, one could ask, if there's nothing hot enough, does that radiation exist at all? Now, what you see here is a picture in the optical of supernova 1006. It was observed in the year 1006. And the optical, a supernova is an exploding star. In the optical, you just see a little bit of a stretch here, not very impressive. If you look at it in radio, you see this big explosion shell of hot gas, which is expanding after the star exploded. If you look at it in X-rays, you believe to see sort of pieces of matter flying out there. You can superimpose all these to get an even more nicer picture. And since a couple of years, we know that the polar caps of this object glow in very, very high energy gamma rays and radiation, which is at this very extreme end of the spectrum, which is not supposed to happen. So this is a very young branch of astronomy. The first sources were discovered only in 1989, but it has been rapidly growing ever since. So let me just put this on a little bit more scientific terms. What you see here is, again, this sort of cosmic scale. There's a frequency which goes with it, which is the number of oscillation the wave oscillates per second. There's a wavelength of the radiation, and there's the energy per radiation quanta. Our visible light typically has an energy. We use units of electron volt, which is a tiny quantum of energy. Our normal light has about 1 electron volt, has a wavelength which is slightly below a micrometer and oscillates about 10 to the 15 times per second. The radiation which we'll look at today is in this yellow band here. So it has energies which is 1,000,000,000 times higher per radiation quanta than visible light. It has a wavelength which is a fraction of the size of an atomic nucleus. And the radiation sort of makes 10 to the 26, 10 to the 27 oscillations per second. So once more, I'll sometimes mention this unit, electron volt, which is sort of the unit of a quanta, the energy of a quantum of visible light. And what we'll be talking about up here is 1,000,000,000 electron volts. That's also called a tera electron volt, 10 to the 12 electron volts. That's sort of the most extreme kind of electromagnetic radiation one is able to see from the universe these days. So that was one motivation. We're trying to open up a new wave band onto the universe. And whenever you open up a new wave band, you learn new things. There's, however, a second kind of motivation. And this second motivation has a very specific goal. It is the quest for the origin of the so-called cosmic rays. Now, what are cosmic rays? Well, the Earth is continuously bombarded by particles from outer space. These particles, called cosmic rays, are atomic nuclei, so they're hydrogen nuclei or iron nuclei. They have extremely high energies. They reach energies which are many orders of magnitude higher than the highest energies reached in accelerators on Earth. When they hit the atmosphere, when they hit atoms of the atmosphere, these nuclei break apart, and they form cascades of secondary particles. They don't reach the ground. We're shielded by our atmosphere. Now, these cosmic rays were discovered in 1912, over 100 years ago, and even today, we're not quite sure where do they come from. Where are these cosmic particle accelerators which generate cosmic rays and shoot them at us? And gamma ray astronomy, as I'll show you, is one way of addressing this question. Now, why are we so puzzled about the origin of cosmic rays? Let me give you an example. This is a starry sky. And if you want to know where is light produced, you just look at the sky. There are lots of dots. Each dot is a star. Where there are light quanta coming from, there's a light source. Straightforward, huh? Now we do the same thing. We take these particles, these cosmic rays, which hit the Earth, and we just look where they come from. By suitable means, we can measure their direction, and then we make a distribution across the sky, and then we'll see bright spots, and these are cosmic accelerators. So this is what we see. The sky is completely uniform, perfectly to a fraction of a per mil. They come from everywhere with the same frequency. So somehow there seems to be no source of cosmic rays or no cosmic accelerator which we can see. Now, the explanation is actually quite simple. Assuming there would be one of these cosmic particle accelerators, whatever it looks like out there, and it takes an atomic nucleus and it shoots it towards the Earth. Now, an atomic nucleus carries an electric charge, and space is full of magnetic fields. And a charged particle in the magnetic field, like in the old TV machines, is deflected. And so this particle does not fly on a straight path to Earth. It meanders. And by the time it arrives on Earth, it comes from a direction which has nothing to do with the direction towards the source. So we see a completely random, completely flat-looking sky because these magnetic fields randomize all directional information in the cosmic rays. That's why it's so difficult to understand where these cosmic particle accelerators are located. Cosmic rays are quite important. While they meander through the Milky Way for millions of years, they, for example, ionize interstellar gas. They result in formation of complex molecules. So they sort of possibly even drive the evolution of something like life in the end. So for this reason, Victor Hess, who discovered cosmic rays in a balloon flight in 1912, was awarded the Nobel Prize in 1936. So obviously, out there in the universe, there are somewhere particle accelerators which accelerate particles to incredible energy. And the question is, we don't see them. We'd really like to know what they are. Now, one, it turns out, is pretty close by, which is the sun. What you see here is the SOHO satellite. That's a satellite taking pictures of the sun, particularly of the solar corona. The central part is sort of blinded, is blacked out here. Now we take a little movie where you see a solar eruption going on here. And now this is a time-lapse movie. A couple of hours later, this picture has all these kind of very strange, grainy structures. This is, if you look at the time scale, it's a couple of hours later. What's happening there? Well, in the solar eruption, particles are accelerated. They travel for a couple of hours until they reach the satellite, and then they hit the photosensor chip in the satellite. And each time a particle crosses this chip, it leaves a white dot, or if it just flies along the chip, it leaves a line. So the sun is a cosmic particle accelerator. However, as we know nowadays by measuring these particles in more detail, this is a pretty miserable cosmic accelerator. It doesn't reach very high energies. So we need to do something, need to look for something better. And if you talk about accelerators, more energy always means bigger. If you build a more energetic accelerator, it's always bigger. So we need to look for really big things. And one of the big things proposed to be cosmic particle accelerators are supernova explosions. This is Tycho supernova, an exploding star, which was observed here in 1572. It is now a gas ball which has a diameter of 50 light years. It's expanding with a small fraction of the speed of light. And quite early in 1933, Zwicky, a very creative astrophysicist, proposed that supernova explosions are cosmic accelerators based on the argument that they're the only objects which have enough energy to fill the galaxy with cosmic rays. It took quite a while until 1949, until Fermi, another great scientist, came up with an acceleration mechanism, how these objects actually accelerate particles. And let me try to illustrate what the theory is. So this is a supernova shockwave. It's a fireball expanding in space with a velocity of a few thousand kilometers per second. Now, in this fireball are all kinds of magnetic fields traveling along with the same speed. And they're also in the ambient medium other magnetic fields. And as we know, charged particles are deflected in magnetic fields. So what can happen is there's an atomic nucleus sitting there or flying there leisurely around. It's hit by this expanding wave, which comes towards the nucleus. It's kicked a little bit, then it's scattered back, then it hits again some scattering center, some magnetic inhomogeneity out there. It's kicked back and forth, and each time when it's kicked by this expanding supernova shell, by this expanding gas ball, it gains a little bit of energy. So the mechanism is actually, could be illustrated as playing tennis with a truck which is advancing towards you. So you play the tennis ball against the windshield of the truck. Since the truck is moving towards you, the ball comes back with a slightly higher speed than it had before. Now you return it again, and it has an even higher speed. You return it once more. And if you do that 1,000 times, you've got a pretty fast tennis ball. And of course, at some point, the player will miss the ball and the thing shoots off and makes a spectrum of energies of tennis balls of all kinds of velocities. And that's sort of the way how these supernova accelerators are supposed to work. Now, the question is, this is theory. Can we test this somehow? And that's where we get back to gamma ray astronomy. So this is an exploding supernova. A particle is caught in the shock wave, is accelerated to high energies. It meanders through Earth, comes from a completely different direction, has lost all its information. However, once in a while, this particle collides with the gas of the supernova and creates new particles, and some of these particles decay into gamma rays. Gamma rays are electromagnetic radiation of very high energy. Electromagnetic radiation travels on a straight path, so this gamma ray travels on a straight path to Earth, and if we look where it comes from, we can see the cosmic accelerator. So there are two important messages. The one is cosmic particle accelerators generate gamma rays. Wherever there are high energy particles and there's matter, there will be gamma rays made. And vice versa, gamma ray astronomy reveals cosmic particle accelerators. That was one of the driving forces behind the evolution of the field after 100 years after the discovery to finally see the sources of cosmic rays. One of my French colleagues said gamma rays looking at a sky is not your nice, quiet night sky. It's sort of more like the turbulent sky of Vincent van Gogh. You see the region of the universe where there's a lot of motion, a lot of energy to accelerate particles. Gamma ray astronomy traces the energy skeleton of the universe. So really looking at a different kind, different aspect of the universe. So that was the second part of the motivation. The first one, opening a new window. The second one, very specific, targeted as understanding this magic cosmic particle accelerators. Now, if we want to do that, we need to somehow detect gamma rays. We need to build telescopes for this very high energy radiation. And that's what I'll cover in the next slides. And I'll take you through a little tour of astronomy, starting with optical telescopes, which are this visible, detecting the visible light and generating all the nice pictures, or most of the nice pictures which you see. Now, an optical telescope in principle is a very simple thing. You just take a focusing mirror, you put some sensor in the focal plane, and you take a picture. Of course, in reality, life is infinitely more complicated, but the principle is really simple. Things get, if you now move up on this cosmic scale, up here, roughly this would be X-rays, the X-ray domain. Things get more complicated because X-rays are absorbed in the atmosphere. They don't make it to Earth, so one needs to detect them in space. That's the first thing which makes life complicated. The second thing which makes life complicated is that there are no mirrors for X-rays. If X-rays hit a mirror, they're just stuck. Now, fortunately, one can reflect X-rays if one reflects them if they hit a metal surface under a very shallow angle, and then they are slightly bent and slightly deflected. And one can use such concentric shells to focus X-rays and to make pictures in X-rays. So that's how X-ray astronomy works. Now, we want to move up even further to the very highest energy, to the right scale of this cosmic piano. And then things get a bit more complicated, even more. Gamma rays are absorbed in the atmosphere. They don't reach the ground. And there are no lenses or mirrors which one could use to focus gamma rays. So what can one do? The first thing is easy. We just go in space. The second one is a bit more complicated. And the way to address that is sort of a brute force approach. One takes a stack of iron plates, about 30 centimeters of iron plates, and puts them in the path of the gamma ray with some detector elements. This is some kind of track chamber. in between. And you see that this gamma ray comes here, it generates a cascade of secondary particles, which you see here, which then is slowly absorbed. So what's happening is the gamma ray up here converts into an electron and a positron. In the next iron plate, they again radiate gamma rays, they convert again. So you get an entire cascade of particles. And of course, you can just now point back this cascade and see where the gamma ray came from. This is the principle of the Fermi Gamma Ray Space Telescope, a really great instrument which has made tremendous scientific impact. It's about a square meter size. It flies a converter where gamma rays convert into two particles, and then down here is a shower where the particle is absorbed. This is a picture of the Fermi instrument as it was built. It's quite interesting. The three gentlemen here are Bill Atwood, Peter Michelson, and Steve Ritz, who sort of are the inventors of the instrument. Of course, they just are there in post, and of course, there's one person out of four working, and it's not known who the working person actually was in this picture. But you see sort of the size of this instrument is about a little bit over a square meter. It was launched in June 2008, and unfortunately, I don't have the time to tell you about the great physics that it has done, because if you want to really go to the rightmost end of this scale, this instrument runs into a problem, which is that these very high energy gamma rays are rare. They come sort of at a rate of maybe 1 quantum per square meter in year, or 1 quantum per square meter in century. Now, if you've got a square meter sized detector, and you wait a year for 1 quantum, it's maybe just barely acceptable. If you wait a century, it's really bad if you're trying to do a PhD thesis. So obviously, one needs bigger detectors, and something which is a square meter won't do. Now, let me just explain why these are so rare. It's not a surprise, it's quite natural. Because the universe has a certain amount of energy. Take, for example, 1 erg of energy. 1 erg of energy are about 10 to the 12 electron volts. Out of 1 erg of energy, you can make 1 million quanta of normal light. You can make 1,000 million quanta of X-rays. You can make 1,000 quanta of the giga-electron volt energies, which Fermi detects, or you can make 1 tera-electron volt, 10 to the 12 electron volt quantum. So it's no surprise that at these high energies, you got a lot less quanta than you got at low energies. The reason is simply the same, why there are a lot more mosquitoes than elephants on Earth. So obviously, with a square meter instrument, we're not going to get very far, and we need to have something bigger. And the idea is now the following. We need 30 centimeters of iron. Flying a football field of 30 centimeter thick iron in space is something which you cannot do right now. However, we're here at the bottom of the atmosphere, and the atmosphere has a column density of 1,000 grams per square centimeter. On each square centimeter here, there's a kilogram of atmosphere. Now, a kilogram of atmosphere is about 130 centimeters of iron. So we don't need to put iron in space. We can simply use the atmosphere, and the same particle cascade will develop in the atmosphere. We only need a way to detect it. And the way to detect it is that these particles, when they rush at speed of light through the atmosphere, they emit a bluish light, so-called Cherenkov light. It's beamed forward like the headlights of a car at a rather small angle. It's emitted, it's kind of the optical equivalent of a sonic boom. It was discovered by Pavel Cherenkov, who for that got a Nobel Prize in 1958. On the ground, it sort of illuminates what we call a light pool of about 250 meters diameter. And you may already have seen, or at least seen on pictures, Cherenkov light, if you've once seen pictures of a nuclear reactor core cooling down, there's always this bluish glow. That's exactly the same. This is high energy particles rushing in the ambient medium, generating this bluish kind of light. So it's exactly the same light, except here we use it to detect these particles. So the effect of the cascading of gamma rays in the atmosphere and the Cherenkov light is that a gamma ray leaves kind of a bluish, really a meteor track in the atmosphere. Now turns out it's very faint. It's a few photons per square centimeter per square meter out of this meteor track, and it's very short-lived, some nanoseconds, some billionths of a second. So it's not as easy to see as a normal meteor track. But the principle is the same, and let me just summarize it in this slide. So gamma ray enters the atmosphere, generates a cascade of secondary particles. These emit bluish light. The telescope takes a picture of this cascade, which is sort of a track, which we see in this photosensor, and we just extrapolate the track back to space, and we see where the gamma ray came from. Now, the one thing which is important to understand is that these telescopes don't take pictures of space. They take pictures of tracks in the atmosphere, meteor-like tracks. And we point back, so one picture corresponds to one point in the sky where one of these gamma rays was made. It's not yet a picture of the sky, it's just this picture tells us here is a gamma ray coming from. If we want to get a picture of this gamma ray sky, what we need to do is wait and accumulate many such pictures and superimpose them, and then slowly, as we collect more and more of these gamma rays, some kind of picture of a celestial gamma ray source will emerge. Like it's here, this is a simulation one of my students generated. And of course, as you might recognize, this is not a celestial object. It's simply the logo of our institute, translated how it would look like if you see it in gamma rays. Okay, but that's the principle. So these are non-trivial experimental efforts. There are right now 3 big telescope systems which do this science. One is the high-energy stereoscopic system called HESS in Namibia, the MAGIC telescopes on the Canary Island of La Palma, and the Veritas telescopes in Arizona. Now, for Spain, of course, not only because of the location, but also because there's a very substantial and important involvement of Spanish scientists who've moved this telescope and this science forward. Of course, for Spain, in a sense, the most important is this MAGIC telescope on La Palma. On the other hand, I work for, or with, or have founded maybe, the other experiment. So what I'll tell you in the following uses pictures from HESS, but sort of the science and the principles is the same, and they're both very successful. To get there, you fly to Windhoek, which is the capital of Namibia. Then you drive for about an hour and a half on a gravel road into the so-called Comas Highland. You should not get distracted by the wonderful dunes of the Sosufle, which is a little detour. You should also not drive too fast. We typically lose 1 car per year because, I mean, these are gravel roads. The first half hour you go at 60 kilometers, the next half hour you go at 80, then you go at 120, and then you hit a sand pit or something. We tell our people go slowly, some do, some don't. Fortunately, nobody was seriously injured. Well, assuming that doesn't happen to you, at some point you see the plateau of the Gamsberg at the horizon. This is a table mountain which was once meant to house the European Southern Observatory. For various political reasons, it didn't come to be. But it's well known and an excellent spot for optical astronomy. And at the base of this table mountain are our telescopes. So this is one of these telescopes, which we built there. It has a big mirror made out of multiple facets for cost reasons, focusing light on this light sensor, which we call the camera. And of course, it has a telescope mount, which allows it to point at any place in the sky. And this camera here is a bundle of so-called 1,000 photomultipliers, about 2 meters across. I'll get back to that. So let me just show you, this is a picture from the inauguration in 2002, which gives you a bit of feeling for the size of these telescopes. So just to relate how these telescopes functions once more to things which you're probably more familiar with, a photographic camera, our mirror has 100 square meter collection area compared to a few square centimeter of your typical photographic lens. Our photo sensor is this bundle of photomultiplier tubes rather than a silicon chip. One of the reasons is that we need a big sensor. It has about a square meter area, whereas the silicon chip in your camera has a few square centimeters. Where your camera really excels, however, is the number of pixels. Typical camera has 20 plus million pixels. Our telescopes take relatively coarse pictures. They have only about 1,000 pixels. But what they do is they allow very short exposure times, essentially of the order of 10 to the minus 8 seconds, 10 nanoseconds, whereas your normal camera goes down to maybe a thousandth of a second. And these short exposure times are very crucial, and they're also demanding. Why are they crucial? Well, this is a picture of the sky taken with an exposure time with a 100 square meter telescope of 1 millisecond, sort of the limit of a modern camera. And what you see is nothing. You just see noise. And the reason is if you have a 100 square meter mirror to collect light, even a seemingly dark night sky is not so dark. There's a lot of photons coming from the night sky. The only way you can get rid of that is making the exposure time shorter, because the light from the cascade arrives in a very, very tiny light interval. And if you catch just this interval, the thing gets better. So now if we take a microsecond, the millionths of a second, oh, maybe there's something emerging. If you go down to the 10 nanosecond exposure time, then you see the image of the air shower. You also see that it's a relatively coarse pixelization. So we don't resolve these images terribly well, but sufficiently well. Now, the sensors which we use are so-called photomultiplier tubes, and they're connected to electronics which records the signals at gigahertz frequencies, and that allows us these very short exposure times. So again, this is a time-lapse movie of how these telescopes work during night. They point at a certain point in the sky, they track that region of the sky, and they collect all Cherenkov light flashes, which come from that. They're recorded and then analyzed in a computer. Now, we do have not just one telescope, we have 4. The reason is the following. We don't, as I said, we don't take pictures of the sky. We take pictures of the tracks in the atmosphere, and we want to know where these tracks point back to. Now, if you want to know the direction, say, of this pointer, and you close one eye, you see only one projection. You cannot tell, or I could with one eye not tell this orientation. I can tell this one. So you need always multiple views. That's why nature has given us humans 2 eyes. And it turns out in this case, if you use 4 eyes, you do even better. And then we use, instead of a brain, we use computer systems to fuse these images into a 3-dimensional image of the cascade. Now, when we decided to go to Namibia, we're afraid of lots of things. I mean, this is Southern Africa. There are corrupt customs officers. There are lots of poisonous snakes. There are all kinds of big cats around. So we're terribly afraid of what might happen. None of that happened. I mean, we didn't. All the customs officers were fine. All the snakes ran away before human come. None of the big cats was there. What we didn't expect was African bees. They're very angry if you disturb them, and they like to build their nests wherever there's sort of a little enclosed hole or something. And a big telescope has lots of little regions where you can build nice nests of bees. And so our technicians in the end ended up sealing every little possible hole where these animals could build a nest. They get really angry when they're disturbed. Another thing which we didn't expect, these are the mirrors. For cost reasons, we built the mirrors out of small, in this case, 60 centimeter facets. And there are motor actuators which allow us to move these facets to make a coherent image. Now, again, the things had to be cheap, so these are motors which normally move your car windows up and down. And it's interesting, these motors are watertight, because if you run your car into a river, the statement is you should at least be able to open the window once to get out. And so they have little diaphragms about here, which allow a slight humidity exchange between the inside and the outside of the motor to avoid accumulation of moisture inside the motor. And this is sort of a little paper thing. And it turns out there's a Namibian bug which likes to eat exactly that kind of paper. So the bug ate all these little diaphragms in our motors, water got in, and we had to exchange a few thousand motors and clean them. And so the bad things we expected didn't happen. a lot of unexpected things happened. But overall, I must say it was a very pleasant experience. So now, of course, the question is, what do we see? How does the sky look at these extreme energies? Well, this is a picture of the Namibian sky. You see here the Milky Way, one of the telescopes pointing at the Milky Way. This is how it was in 2002. After 10 years of collecting data, we're able to superimpose on this optical image an image of the gamma ray sky, and it looks like this. So you see in the Milky Way, contrary to the optical, where it's sort of a diffuse structure, you see it very clearly lined all along the Milky Way. There are TV gamma rays, very high energy gamma rays produced, which means all along the Milky Way are cosmic particle accelerators. That was the first big surprise of this thing, because before one was expecting that sort of particle acceleration in the cosmos is a very rare thing. It happens sort of after a supernova for a short time, but that's it. That's not the case. The whole Milky Way is full of cosmic particle accelerators, and one can identify individual objects. They got names which say, they're called, you can't read it, Hess, J something or other. Hess means we've discovered it. J something or other is the coordinate where the thing is. And I said each of these objects is a cosmic particle accelerator. Really surprising that in a domain where one would have expected to see a handful of objects, one sees quite a large number. Just panning along the Milky Way, you see these objects, you see that they have rather complex shapes. Most of them, sorry that this is not moving quite smoothly, most of them actually are fairly big. In real life, they're tens of light years across, so they're really huge gamma ray emitting regions in our galaxy. And just to illustrate how this field has evolved over the last 2 decades, 1989, I mentioned it, the first object was discovered. Nowadays, we're approaching, this is not quite up to date, we're approaching about 200 objects. So what started as a rather exotic search has really become a new branch of astronomy. And I take a certain pride that with our telescopes, we've discovered about 2/3 of the known objects in this energy range. What was also nice that in a study of scientific citations, these telescopes were in 2009 ranked among the top 10 observatories worldwide, together with the ESO telescopes, together with the Hubble Space Telescope, together with other telescopes which cost about 1,000 times as much. That was a really nice success, and it sort of signals that there's a new field of astronomy on the rise. So the first question is, of course, theory tells us, and I showed you this mechanism of the moving truck, that supernova explosions and what's left after a supernova explosion, these gas balls accelerate particles. I've shown you that one. This is supernova 1006. It's in our galaxy about 1,000 light years away. And yes, it glows in gamma rays, so there are very high energy particles accelerated in the 2 polar cups of this remnant, not all around. One can understand that it's a little bit too complicated to discuss it right now. Another object is this one, which has the nice name ARCS-J1713. And here, for the first time, we're able to see in gamma rays in the shell of a supernova remnant. This thing, if you could see it with your eyes, would in the sky be about as big as the moon. And this very clearly demonstrates that there are very high energy particles being made all around the shell of this remnant. So the supernova remnant is very clearly accelerating particles to extremely high energies. Supernova explosions are cosmic particle accelerators. Now, we're still grappling with some of the details, whether they really explain quantitatively the flux and the energy spectrum, but I'll gloss a little bit over that and tell you what else we see. This is sort of a 2 degree by 2 degree region of the gamma ray sky. Again, a region in our galaxy about 1,000 light years from us. And here we see 3 objects. In this case, the color, normally color encodes intensity. Here it encodes the energy of gamma rays. So these objects emit somehow different energy. Gamma rays, if you ask what is there in the sky, it's not a supernova remnant. It's a pulsar, another pulsar, and a pulsar in a binary system. So somehow, pulsars accelerate particles, and a lot of the sources are such objects. How does that work? Let me just explain to you what a pulsar is. So this is a supernova explosion. Now, sometimes when a supernova explodes, part of the material collapses to a very dense, so-called neutron star at the center of the supernova remnant. So this would be a neutron star. This has the mass of the sun, roughly. It's condensed to a 20-kilometer size. It's the density of an atomic nucleus. In the process of condensing it, the sun, or the star before, rotated rather slowly. Stars rotate relatively slowly. Now you bring all this material together into a very small volume. And you know that from ice skaters, if you do a pirouette and you move your arms towards your body, you spin up. And exactly the same thing happens. Now this thing spins up because it shrinks by well over a factor thousands in size, so many thousands. It suddenly rotates about 10 times per second or even faster. So you got a compact object, the mass of the sun, rotating 10 times per second or faster. And also the sun, before it collapsed, or the star, had a magnetic field. This magnetic field was distributed all across the surface. Now suddenly all collapsed, and all the magnetic field lines need to come out of this little body, which means there's an incredibly dense bundle of field lines out there. And so the magnetic field is a million times bigger than the magnetic field we have here on Earth. These are some of the biggest magnetic fields in the universe. So what we have now is we have a very compact object with a giant magnetic field, and it rotates, it spins that giant magnetic field through space. And whenever you spin a giant magnetic field through space, you basically got something which behaves like a dynamo, the dynamos which you used to have at your bikes, at least in the previous generation. Again, there, something rotates, there's a magnetic field, and generates electric voltage. Now, your dynamo on the bike generates about 6 volts or so of voltage. If you put in the numbers, the size of the magnetic field and the speed at which this rotates, you come up that this generates a voltage of about 10 to the 14 volts, 1 with 14 zeros. And in a potential of 10 to the 14 volts, you can terrifically accelerate particles to very high energies. Again, there are lots of details which we don't understand, but that's sort of the basic idea. This thing is an incredibly powerful voltage source, and that voltage accelerates particles, and that particles make gamma rays. And for example, this object here, again, this is a pulsar, and that feeds with accelerated particles the region which is about 100 light years across. So you got a big ball of about 100 light years across, filled with high energy particles, pushing all the other material aside, being fed from this pulsar. So in total, we have about 80 or so objects in the Milky Way. They're binary stars which rotate around each other with a period of a couple of days, which produce periodic signals. They're the shells. They're the pulsars. There are cases where inside a supernova there's a pulsar. There are a few cases, or in fact sort of half, where we're not quite sure what it is because there are too many possibilities. What's also interesting, there are few where we don't see anything. So there are gamma rays which come from a region of the sky which has no object which we believe can accelerate particles and make gamma rays. So there's something, either we haven't looked deep enough, or there's some mysterious other mechanism like dark matter annihilation which generates gamma rays. We'll see. Now I should say current instruments, this is the distribution of gamma rays, of gamma ray sources in our galaxy. And you see that we sort of see the solar neighborhood. We don't look very far away. That's not because there are no cosmic accelerators elsewhere in the Milky Way. It's just because our current instruments are not sensitive enough to look very far. So we can look a couple of thousand light years. The more surprising is that there are other kinds of sources which are 100 million light years away, extragalactic, much, 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 much further away. And one of these objects I want to discuss is something called PKS Parkes 2155. It's an object in the Parkes catalog. If you look at it in the sky, it's just a little star. Looks like a little, well, not very interesting. If you look at it, well, what this, however, is, it's a galaxy which at its core contains a supermassive black hole of a mass of about 1 billion, an English billion, I tend to get confused, solar masses at the heart of a galaxy. Now, you'd think black holes are called black holes because they're black. So why should this thing emit anything? It's a sort of common misconception that black holes are black. Out of a black hole, nothing can escape. But if something falls into a black hole, while it's falling, it emits a lot of energy. So in fact, some of the brightest objects in our universe are black holes. If you have a well-fed black hole, which accretes lots of stars and material, it even produces these jets. So not all the matter falls into a black hole, but at nearly the speed of light, matter is expelled from the black hole in the form of a jet. And all of that is glowing in all bands of the frequency range. So black holes are really typically not black. And one of these objects, this is the object PKS 2155 I told you about. This is the gamma ray flux, which we see from this thing. There are two things which are remarkable. One is, if you take the amount of energy in these gamma rays and you know how far the object is away, and you calculate how much energy it produces, then it produces about 100 times the luminosity of our galaxy. So the thing in these extreme energies is 100 times more energy outputting than our entire galaxy. The other thing which is remarkable, this is a time scale in minutes. So the emission changes on a time scale of 2 minutes or so by a significant amount. Why is that so amazing? Well, let me give you an example. This is our galaxy. We're here. Let's assume somebody were to turn off all the stars in our galaxy tonight. Some evil being. The question is, what would we see when we look at the night sky tomorrow? So somebody turned off all the stars in the galaxy. This is the night sky today. How would the night sky look tomorrow? That's how it would look tomorrow. Exactly the same. That's how it would look in a year. That's how it would look in 10 years. Hasn't changed. Why hasn't it changed? The reason is the nearest stars are many light years away. So the light from the stars travels years before it comes to us. And if somebody turns off a star, it will be years until we notice. In fact, it will be, for most of the stars, hundreds of years, or even thousands, or 10,000s of years. So the galaxy is about 10,000 light years big. If somebody turns off the galaxy, it will take 10,000 years until the light from the stars shuts off, because the last ones take 10,000 years to come to us. So what does that mean? It means if somebody can turn it on and off on a time scale of 2 minutes, it cannot be much bigger than the distance light travels in 2 minutes, because otherwise we would see the light coming from the back side while the front side is already turned off. So we have an object which has a size of about 2 light minutes or so, which is about the size of the solar system. And that region outputs 100 times the energy of our entire galaxy. And it switches it off on very short time scales. And I would really be very happy to know how it does that. It's an incredible energy machine. We're trying to understand them, but we aren't quite there. Let me just, before I come to a preliminary conclusion and give you a bit of an outlook, briefly mention, of course, we do have a not quite as massive black hole at the center of our galaxy. The center of our galaxy is roughly here. And the question is, shouldn't we see that black hole? Shouldn't that be outputting a lot of energy? Now, the answer is that one is a bit of blacker hole because there's just not a lot of matter falling into it these days. Probably 100 years ago, it was different, but these days there's not a lot of matter falling into it. But nevertheless, it turns out it is a particle accelerator, and a fairly strong one. This is now an artist picture of what we understand from our observations of the galactic center. So there's a very strong particle accelerator sitting at the very galactic center, at or surrounding this black hole there. It accelerates particles to very, very high energies. These particles then interact in the dust torus, in this torus of dust, which surrounds the central black hole, and turns that torus into a very intense gamma ray source. And the intensity of cosmic rays of these high energy particles in the galactic center region is about 2 orders of magnitude, 1 to 2 orders of magnitude higher than the density of cosmic rays here, because this is such a powerful cosmic ray source. So yes, our own black hole does accelerate, it does convert energy. It's just not being all that well fed, but that may change on time scale of even years or hundreds of years. So let me come to a preliminary conclusion and then tell you a little bit about the outlook. So gamma ray astronomy at these extreme 10 to the 12 electron volt energies opens up a new window onto the universe, onto a different universe of cosmic particle accelerators. And one of the big surprises was that particle acceleration happens everywhere throughout the universe. And we know nowadays that without these particle accelerators, our galaxy would look different. So it is not a little side effect. It's something which is turning around a lot of energy and which is influencing the way the universe evolves. So this is, again, coming back to Vincent van Gogh's picture. One sees the places where there's a lot of energy being dissipated in the universe. We do have a qualitative understanding of the mechanisms, but we have a long way of really quantitatively understanding how these accelerators work and how they impact the evolution of galaxies. And there are lots of other interesting questions which I couldn't cover. And basically at this point, we're sort of restricted by the sensitivity of our instruments. I showed you that we see only a part of the galaxy. So our chairman was friendly to say that our telescopes are among the best in the world. If you have the best telescope in the world, what do you want? An even better telescope, of course. I mean, that's normal for astronomers. So a little over 10 years ago, we thought about how can we build an even, and of course here, better means bigger. How can we build a bigger telescope? Okay, so you dream of an even bigger telescope. Now, and the question we asked ourselves in 2003, how can we build a big telescope without it being incredibly more expensive? A telescope consists of a mount, which is called a steel structure, a mirror, and a photosensor. And you can ask, how do the costs scale if you build bigger telescopes? It turns out the mirror just gets more expensive as the area grows. The photosensors get very little more expensive. What really costs is the steel structure, which essentially decreases like the third power of the size because it's a volume. So we thought, is there any way to get rid of the steel structure? Well, there's the Arecibo radio telescope, which is a big dish dig into the ground, and then you have a receiver, and instead of turning the dish, you simply move the receiver. It's very nice, works for radio telescopes. Unfortunately, the optical requirements, the imaging requirements are not such that we could use it. So the next thing we thought about was a Schmidt telescope. A Schmidt telescope is a nice thing. What it does, it has a slightly bigger mirror than it needs to, and the camera just looks at a certain part of the mirror. If you want to look elsewhere, you use a different part of the mirror. Gets rid of the mount. The problem is now you need a much bigger mirror than you would have needed otherwise, and all your financial advantage is gone. Then we came up with the hexapod idea, which has been realized for small optical telescopes, which is you use 6 hydraulic actuators to be able to move a telescope dish around. Now, in our case, this is a 100-ton steel structure, which is about 30 meters wide. So moving that on hydraulic actuators, sort of in roughly that speed, that's about real time, is not completely trivial. After quite some search, we found a company in Austria who actually designed the hydraulic system capable of doing that. And we looked at that, we discussed it, and we got scared. Yeah, I mean, this thing is pumping cubic meters of oil around. If there's a little leak somewhere, just the safety system avoiding the whole thing tilting over. So in the end, while this was a little bit less expensive, we were so scared that we reverted back to the design and rather tried to get a bit more money. So that was the design which we had in 2003. This is the telescope we had in Namibia in 2012. This is the 4 already big, as you've seen in picture, telescope which we used since 2002. This is the largest such telescope on Earth, a 600 square meter dish and a very fine resolution camera. And let me just show you a few pictures from the construction of this telescope, because that was quite an experience. So here you see the steel structure. This looks a little bit odd. What this is the mirror dish, the structure which holds the mirror, and what this is the mount which serves to turn the telescope around. Now, normally what one does is one assembles the dish on the side and then lifts it into the mount. It's much easier than building the dish inside the mount. Why did they do that? Well, the reason is there's no crane in that part of southern Africa strong enough to lift this 60-ton dish up. And just to give you a feeling for how big the telescope is, this is sort of the elevation bearing with a little working platform. You zoom in, you see a few people working there. So it's really a big structure. And the idea how to pull that up was sort of something which has never been used for telescopes. What you see up here are hydraulic actuators. And the way they work, they're basically steel ropes going down to the dish. And the idea is now you have a hydraulics which grabs the rope, lifts it up a little bit, then the next come lifts it up, the one grabs around, and so on. Had never been done before for a telescope. You see here Renate Schmidt. Renate Schmidt, she is the head of the Namibian Engineering Association and the lady who designed the telescope. And this was the moment when the dish was supposed to go up. And she obviously looks just a little bit skeptical, but it turns out it worked just fine. I mean, this was sort of a morning in 2011. And the thing, of course, this is a bit of time lapse. The whole thing took about 8 hours or so. The thing moved up. It got stuck here a little bit and took a little bit of a kick, but then it was fine. And as I say, it was the first time something like this was done, was such a structure. Then one has the dish hanging up there. One needs to turn it around, mount the mirrors, and then this telescope, again, this is a time-lapse movie, is in operation, and we've shown first results at conferences. So this made the best instrument in the world even a little bit better. But in this field, I mean, the lead times are long. It took us 10 years to build this telescope. So rather soon after that, we started to think ahead. And what do you want if you have big telescopes? Many big telescopes. Even more sensitive, even better, even bigger. Well, didn't get quite there, but not too far. So in November 2005, we submitted a 5-page letter, 5-page proposal to the European Commission saying we want to build a large array of such Cherenkov telescopes to push our knowledge even further. And we want to build it as a European science infrastructure. Well, then basically a lot of paperwork and a lot of research work converted this into what we now know as the Cherenkov Telescope Array, CTA. It is a worldwide consortium of scientists driving this development. 32 countries, all the ones marked in blue here, over 200 institutes, over 1,300 scientists and engineers. Essentially, the worldwide community working in this field is participating in this instrument. Should also say there is, recently the sites were chosen. There will be 2 such instruments, one to cover each hemisphere. The northern one will be on the Canary Islands in La Palma. The southern one will be in Eso in Chile, which means all of us will have to learn Spanish, obviously, to visit these sites. And I should mention that there's a very strong Spanish contribution to CTA. As I mentioned already, Spanish scientists have been driving this field forward for a long time. They were central in the evolution of the field. There's a significant number of institutes of Spain, here from the Madrid region, from the Barcelona region, and from elsewhere, involved in this enterprise, and of course was instrumental in convincing us to host the Northern Array on La Palma. So this is where the Northern Array will be built. These are the two magic telescopes of our colleagues, and basically will fill this entire plane with telescopes. The hosting agreement with the Instituto de Astrofísica de Canarias was signed in September this year, and in fact, construction has already started for the first really large telescope. This is how it will look like in a year from now, with a 23-meter diameter dish, able to point at any point in the sky within 20 seconds. So this big structure moves at incredible speed to be able to catch transient sources. The counterpart in the southern hemisphere will be located on the area of the European Southern Observatory. So there's Terra Paranal, which has the very large telescope, Terra Amazonas, where the even bigger telescope, the future ESO telescope, is being built. And our telescopes, about 100 of these telescopes, will be sited in the valley in between, making use of the existing ESO infrastructure. So basically, the outlook is that hopefully by 2022, we'll have now not just 4, but large arrays of these telescopes operational, giving us a completely, an even deeper view at all these new phenomena, and hopefully helping us to really understand. I mean, right now we see there are lots of new phenomena, but we don't understand them in detail. And the hope is that with that instrument, we'll come to a very detailed understanding. These telescopes combine, these arrays combine telescopes of different sizes for wide energy coverage. And this is sort of an artist's view again of how this could look like. So there's some event happening in the sky, sending out gamma rays, and they make these blue light flashes, which are then detected. So I trust that with this new instrument, we'll push the field even further. It will be an observatory where you can apply for observation time. It will be an open observatory, and it will really put very high energy gamma ray astronomy into the mainstream of astronomy. So thank you very much for your attention.